should reliably complete that sentence. And then unlike your smartphone, which is also trying to do this autocomplete, it's going to complete it with whole sentences and paragraphs. Sorry. Where's the mouse here? That's on this computer, not on my computer. Got it. Okay. So it says I'm an associate professor of computer and information science in Cs. I'm an expert on natural language processing, machine learning, and artificial intelligence. And I've authored over 250 papers, not yet, but thank you, GPT. He's co-authored a book on machine translation, also factually incorrect, but surprisingly plausible. Like I've done a lot of work on machine translation. So this is one interesting aspect of these that I think are important to know for everyone. Like if you get the word out to fellow students. If you're using ChatGPT for your homework, make sure that what it's generating is actually correct, because they're not grounded in anything. So here's an example of what's happening. So here I've highlighted the words based on the probability according to the model. So it's saying something also factually incorrect here. It says that I'm the director of the NLP group, Natural Language Processing Group at IRCS, which is not true, and IRCS doesn't exist anymore, but that's fine. And so each of these words is colored according to the probability that the model assigns it, given in the previous context. Right, so we can mouse over, oh, that's the prompt and that's the completion. Those are good vocabulary. So we can say, what is this accomplished? So it thinks I'm not very accomplished, or with low probability, I'm not a very accomplished thing given this sentence. It would be better to call me knowledgeable or whatever, but it's sampling proportionally to the probability that it assigns to the distribution over all the vocabulary. Okay, yeah.
Does it like do this one word at a time?
It does, yeah.
Okay, yeah.
So it's called autoregressive models. They're predicting one word at a time, and then using all of the previous context that's been either that you provide as a prompt or that it's generated so far to condition to predict the next word. So one of the amazing things about this is the amount of context that it can condition on is huge compared to what we used to have. So we've had language models since the 1990s. We used to previously condition only on a small number of word tokens, like 2 or 3 to predict the next word. Now we can condition on thousands of words, which is really impressive. Okay, so prompts, completions, sampling from the probability distribution over the vocabulary given the next word. Another cool thing you can do with these models is you can change your prompt to do something called few-shot learning. So this is one of the amazing things where we've trained these models on tasks, like mainly continuing text or filling in the blank, sometimes adapting to other specific NLP tasks. And then you can, they are pre-trained, meaning all of the parameters from that pre-training are kept in the model, and then you can apply them to new tasks. So I'm going to say, here's a new task that it's probably never seen, which is I want to build up a table of a professor, a university, and the department that they're from. In a machine learning task, you would normally need like thousands of examples. This is probably a bad machine learning task in general, but here I'm just giving it 4, and then I can say like, okay, now that you know that pattern, I'll give it a stop sequence here. Tell me where Chris Manning is from. And then so that's now my few-shot prompt plus my input. Oops, I had a stray new line there. Let's try that again. So it tells me that Chris Manning is from Stanford University, which is correct, and he's in the computer science department. So it's picked up the pattern and tried to complete it. Yeah. Say that one more time.
So the probability of like you show the word.
Yep.
So out of the 20 words, only one of them has 5% calibrated. The probability of using a word.
So that yeah. So it's trained on a loss function where it's trying to correctly estimate the next word over a trillion words worth of text. So it's trying to accurately predict what next word will come. So it's got a probability distribution over all the vocabulary, and that will change on each time step because the conditioning history has changed. So you could think about it as calibrated during the pre-training phase, but this is also reflecting to you what it thinks is the next word that's likely for it to generate. And then there's some factors that you can control how far down in that distribution it goes. So there's like a temperature parameter here, where if you lower it to 0, it's only taking the single most probable thing each time. If you increase it to 1, it's sampling from the entire distribution, including super low probability things that are in the long tail. And that can affect how plausible it reads to other human beings. So that's one hyperparameter of these kinds of models. The other direction. If you decreased it to 0, it would deterministically always output the same thing. Yeah. So that's like saying how much, what's the top bit of the probability distribution that it'll sample from. It's kind of throwing away the bottom bit. Okay, and then good. So the cool thing is it like knows things about the world, so it can complete facts that it's acquired over the web. Again, no grounding necessarily in reality, but has a surprising amount of factual knowledge about the world. Okay, so that's prompt completion. This is a few shot example where I give it a few examples, 4 shots. And then I have a prompt or a set of prompts and their completions. Once again, same setup as before. It's just trying to predict the next thing. But now it's recognizing I want this table structure with 3 fields, professor name, which I've given as the prompt or the input, university department. The other cool thing you can do with these models is called fine tuning. So the advantage of these few shot learning examples is you radically decrease the amount of data that you need for many NLP tasks. So previously, when we built machine learning models, we would train on thousands or tens of thousands of examples. Now, because of pre-training and the knowledge that gets encoded in the models from related but not identical tasks, we can decrease that super radically. If you happen to have lots of examples of training items, you can do what's called fine tuning. So this has a fixed set of model parameters. You can fine tune to adapt to a particular task you want. It could be anything language related. So I did like, let's generate some poetry. So now I don't even need a prompt. I can just say, generate a poem for me. And it'll say, I'm going to generate a poem called My Name. This is the structure of the data I gave it. So I took 5,000 poems from the Poetry Foundation. I gave it in this structure, title, author, themes, poem, and then a poem. And now it can recognize without any few shot examples that I want to generate a poem. And it does a pretty good job. So this is like just sampling from its distribution, creating a new poem from scratch, saying, I'm going to give a poem in the style of Yusuf Omiyaki. That's this poet, an American poet who also changed his name. So the fact that it picks a poem titled My Name is kind of interesting. And then it generates something that seems to be related to the themes that I would imagine this poet has as an African-American poet, right? So it's talking about, I'm the kid who knew the name of all the black fighters and ball players in the newspapers. I was the only one who knew the words of the black preacher. And I was the only one who could say the name of all the black men in the town who I knew. Names meant something, and so on and so forth. So it's generating a poem, and then it's a good style mimic. So I can tweak the prompt. So I can input like, please generate that same poem called My Name in the style of Emily Dickinson. And then my name is a sweet riddle. Tell it to me, I whisper you. And that tells it to me, I whisper you to you. And that tells it, et cetera, et cetera. So kind of in the style of Emily Dickinson, and then I could do it again for Edgar Allan Poe. Very dramatic, very theological. In great beware, know thou my name. Starve not my flame, adorner of shame. I am the gold that lies beneath the midnight mine. I am the dream beneath the tear, the world's desire, the heavens' fire, the love that cannot tire, the passion of the earth, the grave of all things dear, dust beneath the door, tuned without a tone, et cetera, et cetera. So I love these models. I think they're super cool. Like you can do a lot of amazing things with them. I think the fact that everyone's super excited about ChatGPT is unsurprising. For about the past 2 years, every time my PhD students would come in their room and present me with something, I said, have you tried GPT-3 for that yet? It's sort of my cliche approach. Okay, so what sort of cool things can we do with these models? So this being the asset group, I think explanations are a good target. So this is work by my PhD student, Veronica, who's co-supervised by a senior research investigator, Mariana Apidanaki here at Penn. And so Veronica, for her WPE2, put together this brilliant survey of like almost 100 papers in model explanations for NLP. So how do you explain what a model's predictions are? So I totally recommend that you check out her paper. She's submitted it as a survey article to the journal Computational Linguistics. So I think this audience is probably already convinced that explanations are important, but just to make sure we state it explicitly. End-to-end neural networks are awesome. They perform very well for many tasks, but their reasons for their predictions are often inscrutable, right? We don't know why it's predicting a certain label when we're doing image classification. So there's sort of this black box to human beings, and they lack the ability to explain why they made a prediction. So if we were able to explain why a prediction was made, that could help us as model developers debug what's going on, look for things like, are the errors due to weird artifacts in my training data? And for non-experts, it might be able to enhance user trust. If they understand why a model is making a prediction, they might be more willing to rely on its predictions for high stakes applications. Okay, so we're going to say explainability is the extent to which why a model makes a certain prediction can be presented in an understandable fashion to some target audience. And that audience could vary, right? It could be end users, it could be us, it could be whoever. But we want to explain why it makes a prediction. There are lots of different ways that you can try to generate an explanation. It could be done post hoc. You have a model, you have a prediction. You could have a totally external thing that says, explain why this is a good prediction. Or you could have one where it's built into the process. So it could be built into the model. So that's a bit more desirable to have it built in. The other is like, what sort of access does the model have, the model doing the explaining? Can it only see the inputs and the prediction, or does it have access to the full set of model weights? How you display the prediction can also vary quite a lot. So do you show like what input features were active, like where it's paying attention to? Do you show examples of similar classifications? Do you show something called concepts, which I'll go into in just a minute, et cetera? So one of the things that Veronica is focusing on for her PhD is the notion of faithfulness. So I think this is like a key aspect of explanations, and that's if you have a plausible sounding explanation written in natural language, that's not sufficient. Really what the explanation should be doing is reflecting the reasoning process that the model used in order to arrive at that prediction. So you can have very plausible sounding explanations that are disconnected from how the model does arrives at its classification decision. Okay, so that's the little preamble to explainability. So now I'm going to present work from some other PhD students, Yua and Artemis. And this was really led by Mark Yatskar, one of the other NLP faculty members here. He shaped this work and it's really beautiful. I love this work a lot, and I want to give all the credit to Mark and to Yua and Artemis. So this idea is trying to use language models to create something called a concept bottleneck, which I'll explain, in order to do image classification. So we're going to use features created by the language model to predict labels for images, and hopefully in a way that's more interpretable than a black box. Okay? So here's the sketch of what image classification is. We give the model some input image in neural network. It does all of its inference and outputs the most probable label. Right? And these models do great. Like they have very high accuracy on lots of image classification tasks, but they don't really tell us how they arrived at that decision. So there was a model proposed by Stanford from Percy Liang's group, which was called a concept bottleneck model. So the idea is where you should use the neural network is in, given an image, predict each of these human written concepts that are relevant to the class of bird taxonomy. So a human tells you the color of the nape of the neck of the bird is important, the bill shape is important, the head pattern is important. And then the model will just predict these values for this image. And then to perform the classification, you have a very simple linear classifier. So we're bottlenecking, we're forcing the model to go through this small set of human designed concepts in order to make its final classification decision, with the idea that this is now more interpretable than the full end-to-end black box neural model, right? We can sort these by which features are active, if they're binary, or what's the highest probability assignment to them. And you can say, oh, I think that the reason that this is the case is because the model thought that it had a cone-shaped beak and a black breast and so on, right? So there's a couple of challenges with these models. First is like the way that they're originally pitched is they need a human expert to create these concepts, which makes sense. And then they tend to underperform the full end-to-end models. So I would argue here, if we can come within epsilon of the performance of the end-to-end model, even if we're doing slightly worse, this property of more interpretability is desirable, such that it would be better to have a slightly worse performing model that we can inspect than a black box. And that also makes it easier to publish stuff if you're a PhD student. You don't have to beat the state of the art, just make a good argument why not beating it is still important. Yeah.
Something about the previous stuff. When you say that it underperforms the end-to-end, I'm curious, is it because it's misclassifying the concept, or because the concept classifier is?
I suspect that it's because the end-to-end model have access to more features, more elements of the picture than are in this bottleneck, right? Almost by design, we're compressing the set of things that the model in the final layer is able to use for prediction. So that could be good, meaning like we throw away things that are actually spurious features that shouldn't really correlate with the label, but the model's taking advantage of, or it could be bad because we're limiting ourselves to only the things that we thought of when we're designing it. Yep.
Astronomers were happy to put in tons of people out doing it the old fashioned way without a neural net. Now the neural net black boxes are out there.
Yeah, I mean, in the neural network, black boxes are pretty amazing, right? Like, I think if you have lots of data, they are super powerful. Other questions, anyone? Okay, so our proposal is this idea of rather than having a human write the concepts, what if we had GPT write the concepts for us? So we're going to leverage the fact that GPT has some apparent knowledge about the real world and have it generate a set of concepts and then use those as our bottleneck. So now we'll have concepts associated with an image, and we'll still use this linear predictor to make the classification decision to say what kind of bird this is. And we're going to prompt it with things like describe what the black-throated sparrow looks like. So we've got some training data. And now we're going switch from the image to just the text world again. So now we say for each of the classes in our data set, we're going to have a set of prompts, describe what the black-throated sparrow looks like. The black-throated sparrow is a small bird with a black head and throat. It has a white body with brown streaks on its back. The wings are brown with white stripes. The black-throated sparrow has a long, thin beak. It has 2 long, thin legs, et cetera, right? So we have a set of prompt templates that are meant to elicit these kinds of visual descriptions of a thing. What does it look like? Describe the appearance. What's its color? What kind of patterns could we see? Describe the shape of a thing. And there's been some concurrent work that we just found released on arXiv that has an additional set of prompts that are really good. So cool idea. A PhD student from UW had a cool paper on arXiv, like what does a platypus look like, where she did something similar as well. So rather than just using these completions, we're going to try to transform them through a second pass through the language model. Why? Well, there's some things that I think are cheating, right? If I have so first off, we can't just give this whole paragraph of text to the classifier. We need to transform it into features. Most straightforward thing might be just split it into sentences and then use each sentence as a feature, but I think that's not ideal. And it's also cheating. So if it's got the name of the class in it, I think that that's cheating. Like you shouldn't be able to know the thing that you're describing when you describe it. What is a dictionary like? A dictionary is like a dictionary with pages. I don't know. So this, I feel like, would cue the classifier if it's got some data on it to better know the class. Yeah. Did you have a question?
I understand why it's weird, but I don't really understand why that would be an advantage. Thing to you that would have had it come out as maybe do better than you wanted to.
Yeah, so let me try to articulate it better. So we're in the era of pre-trained models, including pre-training for vision, pre-training for language. So if part of our description is, it is this thing, then that pre-training may contaminate our experiments. That's maybe another way of thinking about it, because it may have learned that through pre-training. Another thing that this is now sort of me being opinionated and not really having a good total theory about this, but I feel like long complex sentences are not ideal. I prefer short phrases that are reusable and if it's a long compound sentence with things like and in it, we should split it into smaller chunks. Okay. So we do this transformation using GPT-3, another language model, to generate these things. Then for every concept, we have for every class, like black-throated sparrow, we have 500 concepts that look like this. Maybe that's still too many, so we're going to say, how good is this concept associated with these images that we have from training? So we have a small handful of images, which we know are black-throated sparrows. How good is this concept? It has a black throat. So we're going to measure the similarity of the text concept with the similarity of each image in our data set. We're going to use a system called, so we're measuring the similarity of the target class Y, which is the black-throated sparrow. And we have a set of images that are encoded in our image representation, our image vectors. And then we have a concept, which is written in text. It has a black throat. And so what we're going to do is embed those things in the same space using a model called CLIP, which is also from OpenAI. So the text and the images exist in the same space. Then we can just say, use the text encoder to take that phrase and put it in the same space as the images, and then measure the dot product between them in order to get how similar they are. So we're going to do it for all the images and say, how representative is this text concept of this set of images? Then we can sort all of our 500 concepts. Yeah. X is a vector embedding of an image. Yep. So it's already been encoded by the same process, yeah. So then we can sort our 500 concepts by the ones that are most similar, the texts that are most similar to the images. And on the top, we have a small songbird with a black throat and a gray body, a common bird in the southwestern United States. Very similarly worded one, small songbird with a black throat and a black upper breast. And then all the way down at the bottom, we have things that are either just like not visually salient or are wrong. So it has a thin, high-pitched song, which is hard to hear. May or may not be true, but irrelevant for images. It's not very interesting to look at. A little harsh, but probably okay. It's got poor eyesight. And then this one I think is wrong, a dark line running down the center. Okay, so we've got one way of sorting concepts. And so what we want is not only concepts that are good matches for the set of training images that we have, but also that will help us distinguish against all the other images for all other classes. So we want images that are we want concepts that are able to discriminate between classes. So we're going to do a normalized class association, where the top is just the term that we just defined, and we're just going to sum for this particular class. We're going to say how discriminative is this concept that has a black throat by looking at all the birds in our training data and see how good a feature that is for everything. And we can get a discriminability score for each concept with this negative log entropy. So a higher score here just means it's strongly associated with a small number of classes. So that's like a good distinguishing feature. So if this is a bird data set and one of our features is it is a bird, that's not going to be a useful feature for discriminating between different bird species. Okay. And then we can do this problem of saying, let's pick a subset of those 500 classes so that we have a smaller, reasonable set of concepts. Let's pick a subset of concepts for each class as a combination of things that are highly discriminatable with other classes, and which cover as many of the 500 things as we can, where we've got a facility location function that helps us do that. So it's basically picking out a subset that covers the different aspects of the concepts that we generated. Okay, so here's the whole pipeline. We're going to prompt language models to generate our concepts for each of the classes in our set. Send it off to generate a set of candidates for everything. That means prompting GPT to say, describe what an axolotl looks like. It tells us the axolotl's limbs are thin and delicate and the tail is long and thin. We're going to do a second path with our language model to delete the class name axolotl and to break it into two separate potential concepts. Its limbs are delicate, its tail is long and thin. So that's what we get, a superset of all concepts for each class, and we're going to then try to select which of these we should retain for our final system. So we're going to do that submodular optimization to pick K concepts for each class. So we're going to go from 500 concepts down to, I've forgotten how many, 10, something like that, 50. And we're going to ensure that they're both discriminative and diverse. So we start with this long paragraph-like chunks, and then we have a second one, which is fine-tuned to do this class name deletion and shortening. So it's not prompted, it's fine-tuned. We just did a bunch ourselves. Like we took 100, I think I did them. I was like, I hate these long sentences, let's not do that. And then this is like one place where your professor writes a piece of code for you. It means that they're probably more interested in your research than is comfortable. So I said, go do this. And here's a collab notebook. And then in the end, we've got a set of K concepts for each class that we selected through the submodular optimization. And then we can encode each of those into the joint image concept space. Then we have a test image that we don't know the label for. We use the image encoder that puts it in the same space as the concepts. And it generates a bunch of concept scores that will do like this. Okay. Got the image, run it through the image encoder to get the image embedding. The image embedding is the same as the concept space. And then we don't actually have to predict the concepts for this image. This is not a learned process. We're just saying how similar is each concept to this image embedding. Right? All we have to do is take the dot product. The part that is learned is, given all these scores, like how similar each concept is for the input image, we then want a learned process where we associate that concept score vector with the different classes. So that is learned. But then the prediction is actually quite simple, right? We're just gonna take a dot product of this combination, and then we have a distribution over each of the classes, and we can output the most likely one. Okay. So, yeah. Mhm. Yep.
Not dependent on the visual. How would you distinguish the same word that has context dependency, like apple? Are you talking about a fruit apple or do you context? Well,
Yeah. Yeah, this is great. So let me remember to reiterate the question so that people on Zoom can hear. So the question is, some concepts or some classes are ambiguous, is what we would say in NLP. So apple could either mean the fruits or the laptop or the company. And how do we distinguish between those different things? We don't in this work. So that's a big problem in general. I think so we don't in this work. In NLP in general, there's been a shift from single embeddings per word token or word type rather, meaning like one vector for apple, for all apple kinds of apples, to a dynamically constructed vector in the context of a sentence that it occurs in. So if you said, I ate the apple, it was crunchy and delicious. Delicious, crunchy, ate are all going to influence that dynamically constructed vector for that token. We could probably do something similar here, but we haven't yet done it.
Chris, I have a related question.
Sure.
What if the class is not ambiguous, but some members are missing certain features? So, for example, female black-throated sparrows don't have the black neck, but the black neck is very discriminating. So, what do you do there?
That's a great question, and we have birders in the audience, which is good. So you know more about the concepts than I do. So I think it would depend on how representative our set of images are when we're pulling out the features that are discriminative, right? So I think based on what you're saying, this one in the upper row in the middle column is probably a female black-throated sparrow that's not presenting with the actual black throat. And so the text of the language model might actually generate that. Like that might be described on a Wikipedia page and it might learn that fact about the world. I don't know that it's doing anything sophisticated enough to try to jointly classify black-throated sparrow and gender, especially once we've moved down to the linear layer for classification. So that might be a tricky thing. Yeah. Good insight. Yep.
whether the synthetic content is actually factual or not.
Mhm.
So the features, how do we know they are correct? And are they complete or not?
So to reiterate the question is, I said earlier that language models have a tendency to generate things that are plausible, but not necessarily factual. How do we know that the set of concepts that we're generating are factual or true? And how do we know that the set of concepts that we're generating are complete? And I think the answer to both of those is we don't. We neither know that they're true. We do know that they're visually relevant to the set of training images that we have for that class. And we don't know that they're complete. Yeah, so there would be interesting theoretical work to say, like, how would you do that? We did do a human evaluation to say, for each of the concepts, how well do they ground in the set of images, both for the class that we believe, the class that we're generating them from, and then for a diverse set of classes, for that feature, which images do they pick out? And do people believe that maps onto the visual representations that we're displaying? I skipped those in my slides, but if you're interested, I can pull them out later. Okay, skip ahead here. Okay, so we tested this method on a bunch of data sets from a diverse set of image classification tasks, objects from ImageNet, fine-grained things like flowers, food, birds, action, photos, textures, tumors, satellite images, kind of everything. And we compared against a couple of different things. One is like a simple logistic regression directly on the image features. And the others are sets of concept bottleneck inspired things that use different properties, either human written text or cheating by also using the full representation of the model. And so I'm not going to go super deep into the results other than to say, here's the comparison between the linear probe, not using concepts, and ours. Ours is the blue line. So when we have very few training examples, meaning only a few shots of the image in the training set, we actually benefit from the knowledge that's given to us by the language model. When we get up to the full training set, we tend to do about the same as the full black box classifier, sometimes slightly worse. But again, I promise, like, oh yeah, as long as we're within range of that full end-to-end classifier, it's still desirable to use this kind of approach because it's more interpretable. Okay.
Sorry, flowers is then the other way.
Flowers, which one's flowers? Yeah, oh yeah, so flowers, we do worse on. Yeah. There are other fine-grained ones that we still do better on, like food is fine-grained. The bird types, which is cub, we still do slightly better on. So yeah, I'm not sure that that's the explanation. Okay. We then compared against these other concept bottleneck models. So here's ours, it's called Language in a Bottle, Labo. And then this one was PCBM, I've forgotten which one that is. It's like one is a human written one and one is a automatic one, or one uses a full connection through, it's like an ensemble of the deep learning method and the concepts, which is cheating. Anyway, we do about as well as these contrastive things, slightly better in one case and about tied in the other. So competitive with other things, but now our concepts are automatically generated with the language model and selected through this process. And then the thing that I find it pretty impressive is these are random samples of the decision. So it's not cherry picked. These are like literally, we predict a badger and show the concepts that are most useful for that prediction. It's got short legs and a long body that make it an excellent digger. It's got black and white striped fur. Its coat is very shaggy. Hummus is chickpeas, tahini, olive oil, garlic, and lemon juice made from cooked mashed chickpeas. A horned lark has a black line running through a yellow face. Its head is black with a horn on each side, white horn on each side, black horn on each side of their head. Okay, that's contradictory, et cetera, et cetera. But anyway, there's still work to be done on making these explanations better, but it's pretty promising, I think. Okay. Any questions about that? I'm gonna, yeah.
So I would have thought that the isolation concept would be pretty popular.
Yeah.
How did you manage that trade-off? Or did you have it after?
Artemis or Ewa could explain that better. I was pushing us towards these short descriptions because I feel like there's something about calling it a concept that makes me feel like it should be generalizable, like meaning it should not just apply to a single class. And I was worried that when we were originally using full sentence descriptions, that we're just going to overfit to those sentences and they're going to be some random spurious feature that the model fits to. So I felt pretty strongly that concepts should be short and reusable across multiple classes. But still, we need to do more exploration about that. Other questions? Yeah.
I've got a poorly formed question, if you can
Sure.
hear me.
Yep, we can hear you.
So can you go back a slide to the picture of hummus? Yes, so I guess like, my question is how can we disambiguate between things that are explaining the process of the classifier, which I guess in this case is really very much the clip embedding, and things that are just sort of associated with the clip embedding of hummus, like, you know, like the first line for hummus, it's sort of like the ingredients, which you can't tell from the picture. So it's just, you know, this is just, it seems like this is just telling me that this embedded in clip as hummus, and, you know, clip has some concept of like hummus that includes things like the ingredients.
Yeah, I think that that's an excellent critique. And I think to just make it more in the vocabulary that we're using, are these faithful explanations, right? Like,
Yeah,
concepts that are interpretable, but not necessarily faithful. So yeah, that's a good critique.
and I guess one way of, like, one thing I'd be curious about is what do the explanations look like for things that it gets the prediction wrong for? But like, is it just things that are associated with the label it predicted, or is the explanation somehow pointing you in the right direction for why it got it wrong?
Yeah, that's a super interesting point. I think one of the things that I like about these that we haven't investigated yet, but which I think would be super interesting, is to make the classification process interactive. So to say, here's a picture, you want to know what it is, I give you a list of concepts that I think are active for this class. You tell me, nope, you totally misrecognized that, that's not feta cheese, that's whatever, something else that looks white, it's sugar cubes, right? And then you should be able to see how it changes its prediction as a result of you changing the features that it's using in that decision-making process. Yep. Out of distribution. Yeah, that's a good question. I mean, the other thing that would be really neat is if we could extend this to zero shot, right? So right now we're really calibrating the concepts based on a sometimes small set of images, but you know, GPT can describe something I've never seen. And then could I have a set of, could I then take the image and try to associate it with those things that I've never like selected, or could I have a different process for selecting content? That's similar to what you were asking. Or out of distribution, yeah. I'll let the PhD students answer towards the end, but let me just show off a couple of other quick things that I think are super cool. So this is now less polished, just stuff that we're doing right at the moment, which is like, can we use the same methodology not for image classification, but for text classification. So for IARPA, we're working on a problem of authorship attribution, which has a long history in natural language processing. So there's this really interesting case of the Federalist Papers that are essays that were written by 3 of the founding fathers, James Madison, Alexander Hamilton, John Jay, who didn't appear in Hamilton, trying to persuade states to ratify the Constitution. They were written under a pseudonym, and they're all writing anonymously, so we don't know who wrote what. For some subset of them we do, but there's still 12 letters that are in dispute. And so what we want to know is like, what's the most likely assignment of these 3 authors to those 12 essays? And so we have examples of text that we know that these authors wrote. So this is an example of Alexander Hamilton probably describing Donald Trump when a man unprincipled in private life, desperate in his fortune, bold in his temper, despotic in his ordinary demeanor, known to have scoffed in private at the principles of liberty. When such a man is seen to mount the hobby horse of popularity, to join the cry of danger to liberty, to take every opportunity of embarrassing the government and bringing it under suspicion, to flatter and fall in with the nonsense of the zealots of the day, it must justly be suspected that his goal is to throw things into confusion that he may ride the storm and direct the whirlwind. Okay, this is an argument for creating an impeachment clause in the Constitution. So we've got this author, and then the question is, can we do some sort of analysis of it to say what are the stylistic features that this author uses, and then compare those against the anonymously written essays. So it's called stylometry, trying to do a statistical analysis of the variations in style of a particular author and associating them. So can we input that essay and then get a bunch of concepts related to it? So here's a demo of ours. The author is accusatory. The author is discussing a hypothetical situation, using words related to risk, viewing a situation in stark black and white terms. So these are the kinds of concepts that we generate from text. And the idea is pretty similar to before. We've got a set of prompts. Now we're going to build a set of data that's like an imagined stylometric data set, which doesn't exist, from GPT. Then, unlike the previous work, now we're going to train a classifier. So instead of just using the dot product of the image embedding and the text embedding, we're actually going to try to make a prediction. And then for a new text, like the unknown essays, predict a set of associated style features. Yeah. Yeah, so we do have features in mind. We just don't have any ground truth. So here's what we do. We say, we've got some ideas of like what are important to forensic linguists who do this for a living. They look for things like unique punctuation style. So what we do is we write a set of prompts from these templates, just like describe the visual appearance of blank. Now we say, write a long paragraph describing the punctuation style of this input text. So this is some input text. And then the model says the passage contains several unique punctuation elements, like slash marks and stuff like that, right? So it's a long paragraph. Again, not really good for features. We have a bunch of templates. So we say, write a long paragraph describing the unique stylometric features from the perspective of a forensic linguist who's psychoanalyzing the writer. So that's a different prompt, same text input, and then we say it contains features that suggest the author is tired and struggling to sleep, the sentence structure is choppy, the language is informal, blah, 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 right? So again, we're going to take that and rewrite it using a second pass through the model, saying, write a bunch of short, simple sentences. Now we've thrown away the original passage, and we're just taking the paragraph of stylometric analysis that it generated. Now this is not fine-tuned. This is just prompted. Write short sentences describing the author's writing style based on this paragraph, where each sentence begins with the author uses. The author uses a combination of literary and figurative language, combination of British and American English, cetera, et cetera. So these are features that are generated. And then we try to, now we have a set of a bunch of candidate features and the text that we derived them from. So these are the original input text, like that essay, and then these are the second pass features that got extracted. And so we can create a synthetic data set. So we can say, imagine that all of these labels that we came up with through the 2-pass prompting are actually true. Now we've got the input text and a bunch of gold, silver, whatever, tarnished labels that we could train a model on. So for 1,000 authors and 10 texts per author, 10,000 texts, we're extracting 100,000 of these concepts. And then we have like a 500,000 set of essays paired with concepts. And we can train a classifier, given the original text and one of the features, use that as a training data to predict this feature appears or it does not appear for that text. Okay. And then we've got this nice system called LISA, Linguistic Informed Style Analysis, for an input text. Now that we want to describe, it's a truth universally acknowledged that a single man in a possession of a good fortune must be in want of a wife. For all of the features that we retained, make a prediction, is this feature active for this text or not? So most probable is using words, the author is using words indicating family, the author is using female pronouns, is using words indicating social status, is insightful. So that's what we've got. And this is work in progress. So we don't have any evaluation on how good it is for the application that we actually want to do. We don't know, is this going to work for authorship attribution? But we do have some indirect evidence that these are reasonable. So we collected like 50 different sets of NLP data, each exhibiting some sort of stylometric oriented thing, like texts that are labeled as informal or formal. We feed it one of our features, like the author uses informal language, and we measure how well that feature correlates, the prediction of that feature correlates with the prediction of the formal versus. Does okay. Work in progress. Okay, so eventually what we want to do is use these style vectors for the task of authorship attribution. This is an IARPA project, so there's always a concern that this is a government surveillance panopticon where you will stifle free speech. No one will be able to write anonymous criticism of the government again. This project actually has an interesting offset to that, which is like, we recognize that that's an important thing to be able to do. So in addition to authorship attribution, the project is also investigating authorship obfuscation. So you give me a text and a message that you want to communicate anonymously and evade our authorship attributions. I'll rewrite it in a different style to make it less associated with you. So those style vectors could be used for style transfer as well. And then one last thing that kind of brings it back around to the faithfulness, which is another project led by a bunch of awesome students, including Veronica again, is on faithful chain of thought reasoning. So chain of thought reasoning is taking an interesting observation made by a young guy at Google named Jason Wei, where if you try to get the model to do anything that requires like some symbolic manipulation, like math problems, it falls down. So you can give it few shot prompts like elementary math quiz. So like, here's a question, tell me the answer. That's teaching it. That's the few shot example where you're teaching it what you want it to do. You give it the next question, it'll complete it, but wrong. Okay. So the idea here is let's manipulate the few shot training examples to say, reason out loud. Let's think step by step why I get that answer. So this is not generated by the model. This is inserted by the model designers saying, here for this question, let's break it down into steps, into a chain of thought. Roger started with 5 balls, 2 cans of 3 tennis balls each is 6 tennis balls. So 5 plus 6 equals 11. the answer is 11. That's part of the prompt. And then when you prompt the model that way, it'll also generate its own chain of thought. So it'll mimic what you've done, trying to do the same, and tends to result in higher accuracy answers for these kinds of math problems. Okay. And then but Veronica observes that there's nothing that requires it to be faithful, meaning it can output something very fluent where it's describing its chain of thought, and then output the incorrect answer. Okay, so the cool aspect of this faithful chain of thought is let's translate that kind of chain of thought thing from language onto something that's executable by a symbolic reasoner. So we're going to take your query in natural language. We're going to rewrite it to give the chain of thought, explaining what steps you ought to take in order to come to a solution. And that's going to be a mix of natural language, like in the original chain of thought paper, but also symbols that we can execute. We'll send those symbols to a deterministic solver and get the results. So did this for a bunch of things. You can take a math quiz, translate it to Python, run the Python code, get the output. It's now faithful because the explanation is executable. So there's no way that the explanation is going to be mismatched with the solution. It may be wrong, but it's at least faithful to how it got that answer. They also did Python data log, rule-based symbolic inference, planning domain definition language. So all sorts of cool symbol tools for being able to come up with an executable sequence of thought that has an answer. And they tested this out on a wide variety of problems, including these math word problems that were like everyone started working on when everyone's like, language models are great, but they don't know math. They're so dumb. Okay, that's how do we solve that? Multi-hop question answering, meaning you have to reason through a couple of steps to get the answer. Planning, like you have to come up with a sequence of actions that a robot could execute in order to reach a goal state. And logical inference, they varied the number of few-shot examples and the decoding strategy, and found that overall, their few-shot executable chain of thought models did better than standard, like non-chain of thought prompting models, and better than the chain of thought ones, which were already demonstrated to do better on these types of things. So this is super cool work. Just got released on arXiv. So the neat thing is it's decomposing a task that starts out as natural language onto code or symbolic instructions that are executable. I think there's interesting work to be done on like, how can you work with that translation process? At the moment, they're using Codex, which is a large language model trained on code. But this is a place where we could improve, and showed that it worked for a bunch of different problems and outperformed some other strong baselines, et cetera, et cetera. Okay, so that's all I wanted to present. So if you're interested in any of this work, I stuck the arXiv links up here. There's Veronica's WPE survey on faithful model explanations in NLP. She's also got a great talk on her website if you just want a 40-minute version. There's this draft of our language in the bottle image classification and the arXiv draft of the faithful chain of thought. So thank you.